right, so I think I know most of you, so hopefully you also know who I am. But anyway, I'm Viviana Acquaviva, and as you can see, I'm also not hard. And this is my email address, in case at some point you want to reach out. And so what we have today is a very simple introduction to machine learning. And like I thought about, you could do something simple, but not exactly Coursera-like, although I do like those classes. And so maybe we can discuss together what machine learning is and in what cases it's useful and so on. How many of you have had at least some exposure? Okay, all of you. So like feel free to tell me, okay, you can speed up now, or we can talk about something different. But anyway, so for me, my idea is like this, like what I want to focus on is, imagine that you have this situation where you have some stuff that right? Some stuff you don't know, but you're interested in. And so in this, so we're interested in sort of like recovering, I think I'm gonna fall like 5 times, but we're interested in somehow reconstructing or learning something about this relationship between the input, the stuff that we know, and the output, the stuff that we don't know. And so in this, just by setting the problem up this way, I'm already cheating a little bit, because this is typically predictive machine learning, which is like a subclass of machine learning. And in many cases, this is going to be like a supervised problem, as we'll see in a second. So it's not the most general, but I also felt like unless you're sort of like, exploring the data to discover things, in many cases, this is the things that you want to do. So you can do it in several ways. The first method, and something that we looked at a little bit when we were talking about MCMC, for example, is some sort of model fitting, right? So you can decide, okay, the first thing I'm going to do is in this case, usually the input, we call them observables, right? So again, I worked a long time in SCD fitting, and so for example, for me, my observable would be spectra of galaxies typically. These are the things that like come out from my telescope somehow, and these are the things that I know for all my objects. But what I'm interested in, so the output typically in model fitting language are parameters. So if again, I'm investigating galaxies, I'm like, okay, these spectra are beautiful, but really what I want to know is derived properties, like I want to know like the stellar mass, the age of the galaxy, the metallicity, the dust, content, whatever there is to know. And so how do I go from here to here? Well, first, it's called model fitting. So it means that I need to make a model, right? So the model tells me how my parameters and my observable are related. The model is some sort of function that I try to build using my physical intuition, and that tells me, okay, if your parameters have this value, x, y, and z, what you can expect to find on the observable side is this type of observable. And so actually you have like 2 pieces, a model and a likelihood. The likelihood is the thing that we didn't discuss last time we were saying MCNC, but typically this is the step that takes a long time and it's very complicated. Because what you're doing, again, like with me with a galaxy, I'm saying, okay, this is an object that is super complicated, right? It has like billions of variables, billions of stars. But I'm going to describe it with 5 numbers. And so in some sense, this is, I think, is like both the strength and the weakness of these types of methods, is that one, the strength is like they are built on physical intuition. And this is great. On the other hand, they're really only as good as your physical intuition is, right? And so in some sense, they are subject to all the biases that we have when we are the ones who decide, okay, I decided that if I want to describe a galaxy with 5 numbers, these numbers are going to be the age since star formation began, and the stellar mass, and the dust content that I parameterize in a certain way. So, it's nice because we use physics. But it's not nice because we use our limited intuition. And spelling bee. So, in some sense, if your intuition carries a bias, this is a bias that will be intrinsic in your model. So how do we do this with machine learning? Well, didn't anticipate these boards being so low. I wanted to go on the other side, but then we can't switch the camera. So in machine learning, well, first of all, when you want to make it sound like it's a completely different discipline, you change names to things. So the things that you had called like input or observables, now typically we call them features. And the stuff that you want to know that, like in model fitting jargon are called parameters, typically we call them labels or target. And then, like the new thing that is a bit different from what you do here is that this relationship is not. Actually, we should say it's not maintenance. Right? So you don't write a function that says how your parameters are related to your observable. Well, in some cases you actually do. It's fair to say that like a statistician likes to talk of things like regression. And especially if you're talking about linear regression, you're fitting a line, and you're using exactly the same loss function that we call chi-square. But there are some cases in which you actually are pretty general in how this relationship can work. And so how are you going to learn? Right? It's like, okay, you're not specifying this relationship, so what do? And in this case, what you do is you learn by example. And that's why I'm going to say this was already predictive machine learning, which is at a sub-branch. Now I'm sort of really saying that what I'm talking about is the so-called supervised machine learning. So when you're in a cases in which your machine, your set, is learning because you're showing some examples where both the features and the labels / target are known, this is called supervised machine learning. So what's good about it? Well, let's start with what is not good. So what's not good is that we don't use physics or astronomy or anything like that. And this means that, like the curse, I feel like, of any machine learning methods is how you generalize. Because when you're using a method that builds intuition, and then, when you can convince yourself, whether you're right or wrong, that you've understood what are the important variables for your problems, then it's usually pretty easy to understand how they translate to a different problem in a different domain. I feel like with machine learning, the delicate point is that sometimes it works super well, but it's very, very attached to the data. So it's a good thing, because it's data-driven. And so because you're just learning by looking at the data, this also means that it can be freer from some of the biases that are associated with you wanting to model this relationship in a way that can be wrong or simplistic. However, because of that, you often have this problem that like you need to be very, very careful about the domain that you are applying to. And so an algorithm that is built on certain kind of data will always have issues when you try to apply to different data. And I feel like this is something that, it's not that we try to wipe it under the rug, but I feel like sometimes we underestimate how strong this limitation is. So I don't think really, I have a preference with one or another. I mean, there are like other good things about both of them. Some of the machine learning models, like for example, we heard yesterday from Yasher, are much faster than their like model fitting equivalents. And so this is another thing, like saving time if you're dealing with big data, is something that is big, and you may be willing to take a hit in accuracy or precision because of that. But in general, I feel like that they work best when you're sort of like using them in parallel, or when you can sort of like take advantage of some synergy between the two. So now, learning by example, what does it mean? Well, this is something that we do all the time, right? If I have this beautiful data set, and I show you, these are the examples that I'm going to show you, and in machine learning jargon, this is a learning set. Say, okay, this is my learning set. Okay, so in this case, let's say that my output is going to be the color. This is what I want to learn how to predict. Okay, so what are my features? What things do I know about this data set? About these points?
Clustered.
Right, well, I didn't mean to make so, but yeah, like what I'm saying is like, if I tell you, okay, this is your data set, I'm telling you your output, what you want to predict, your target is the color. What do you think would be the features?
Color.
Hmm?
The color.
Color. Well, the color is what I want to know. What do I know? Like, because, yeah.
The X and Y coordinates.
The X and Y coordinates. So these are like the two things that I know for all these points, and this is already like, a nice representation of the data. I could have given these as numbers, right? And it would have been like much harder to describe this problem. But in this case, I have my two-dimensional, two features data set where I know the X and Y coordinate, and then I'm giving you like 8 examples for which the color is also known. So now the next thing I can do is say, okay, now if I give you a new point, and for a new point, this means that you know the features, the things that you observe, but you don't know the color, and I put it here. Can you tell me what color it should be? Green, right? And so I feel like in some sense, the way that we humans learn is learning by example, is something like rather intuitive. And this is what these others are trying to do. So here is our data. Let's see, what else did I want to say about this beautiful data set? Okay, nothing much, but yeah, I want to show you my favorite examples of like another simple machine learning problem, and like why like the way you write things matters. So let's say that now I'm giving you another one. This one today, okay. One, this is input, and this is output. Okay, so for input 1, your output is 3. Input 2, your output is. Now I ask you, okay, can you predict what the output for 3 should be? For 1 is 3, for 2 is 3. Right, we will guess 3. And this, unfortunately, is not the correct output. And this is because, of course, I've given you only 2 examples. So let me see if I can do a little bit better. And now I'm going to say 3, 3. So I put 2 more examples. For 1 is 3, for 2 is 3, for 3 is 5, for 4 is 4. 4. What did you guess?
It's the number of letters.
It's a number of letters. And so you see here, what I did is like, okay, first of all, I gave you like a slightly larger learning set, which is always better because more examples are better. Another thing that I did, at least I was trying to show is like the way that you write out your data matters. Right? The fact that I spelled them out helps because, it brings your attention to the fact that we're not just looking at numbers, we are looking at strings in this case. And so this part of machine learning, a bit fancier than what I did, is sometimes called feature engineering. And especially if you're not dealing with the most powerful method, like neural networks, which are actually singularly capable at extracting the information in whatever form it is, I feel like a lot of a scientist's work is understanding what are the things that are relevant and how you can represent your data in a way that is helpful to extract the information that you want. And so, for example, here it could have been like, making a plot of this rather than giving you numbers for coordinates. And here it's like, spelling them out as opposed to writing them as numbers. So I'm showing you, hey, the letters are an important property of my data. All right, so far so good. You said you all had some exposure, so I'm sure that everything I said so far is trivial. So let's say that now we have plenty of tools to build machine learning models. And so we have our learning set, say this one. And so the learning set, the labels are available, so you can always pick. And this is what we use to build our model. And so let's assume that you've built a model. Now what? You have used, like there's, if you go to like sklearn, there's like, okay, you can use decision trees, random forest, support vector machines. You can write a neural network in 5 lines of code. So let's say that you build. What should you do next? Can you just like go start using? What will be like a smart thing to do before you give it to someone else? Test. Right? And so, for example, and this is in general good practice in science. So I feel like, again, in machine learning, this is all like this big thing of testing and validating. But this is like, a common procedure of science. If we were doing model fitting, what would we do? Probably we would do simulations, right? Because, since you're sort of like using a relationship between parameters and observables, and, in most cases, you cannot test it on real data, what you do is like, okay, you create simulations and you check that your method is able, at least in the case where input and output are known, to produce the correct result. So here we're doing the same thing. And so the idea is like every time you have a learning set, which means that you have your features here, and you have your labels here, rather than using all of it to build the model, there's always a part that you should, imagine this is an horizontal line. It's sort of like you want to hide it from view for the time being. And so you use this part, which is like the train set, to build your relationship. And then this other part, which is the test set, to check that your algorithm is doing right. Right? Which seems like, an interesting, like an intelligent thing to do. Now, what I'm going to say is like, it may be a smarter idea, rather than just to do this once, and so to sort of like, pick one part of your data set to do it, to repeat this process a bunch of times. Why do you think?
You could have a bias sample.
We could have a bias sample. So one thing is like, okay, if I only do one split, I should say one random split. In general, it's particularly not advised to keep this in a certain order and take some data away. So usually you should at least randomize it, but even one random split is not ideal because it may be a weird combination of like train and test objects. And so this means that the performance that you obtain once you get like certain performance that you obtain on your test set, which is supposed to mimic what new data would be, you may be overly optimistic or overly pessimistic, just maybe because that random split has particular properties. So that's one thing. Yeah.
So when you do this splitting, does that mean that you repeat the training on the new split as well?
Yes.
Okay.
Yes. So this is, and actually I should say here that the purpose of this test set is that you're mimicking new data. So what you're predicting here, which is like the key issue of machine learning, is what I like to call generalization error, or score, which means that basically the performance of your algorithm on the test set is supposed to be a proxy for what the algorithm would do on totally unseen data. And that's, I feel like, a good place to say it. You can see here why even this, which is, something that sounds like a sound thing to do, is already optimistic. Because the train and test set, just from, how the algorithm is built, they truly come from the same distribution. If you have like a bunch of examples and you randomize it and you're taking a random split, you know for sure that these data are essentially the same thing. And so unless, like you're looking at very, very special cases, every time you take these and you apply it to different data sets, there's always going to be some differences. Maybe they come from a different telescope. Maybe the sample is not truly the same. So you want to do your best to make sure that the data that you're applying this to are very similar to this. So you can trust that the generalization error you found in your test set is at least close to what you would find on this new data, that you're not overly optimistic. But, like as soon as you deviate from this distribution, there's going to be like new things that your algorithm has never seen before and therefore may not be equipped to handle. And so I feel like that no matter what, this is the best we can do, but I want to say that it's optimistic. Now, going back to why it would be a good idea to repeat this process a bunch of times rather than do it once. One thing that we said is that maybe this, say that you set aside 20% of your data, and maybe just because of like the random nature of random splits, this data end up having, like a significantly different distribution from this one. Then probably your model wouldn't be too well, and you would be pessimistic because this is not typical behavior, it's a one-time behavior. Another reason for that is that you're not using all of your data in your learning set. And data are expensive, right? And so if you can find a way to use all of them together, that's actually a better thing rather than only using, like 70, 80% to build the model. And finally, I want to say, not only for these, like the performance that we get here is not, it may not be representative, it may not be like your average performance that you can expect, but also you don't get any error bars in that, which is another thing that in science is typically or should be frowned upon, right? So you want an idea, if you say, okay, my test scores, let's say you pick like accuracy, which is just like in a classification problem when your output is finite, it's just a number of correct answers that you get. You say it's 90%, it's much better to be able to say it's 90% plus or minus 5%, and like give a sense of how much that performance can fluctuate as a result of the nature of your data. And so these are all not great. And so the thing that we do, and this we mentioned already when we were talking about model selection a little bit with Hog a couple of weeks ago, is that you move on to a process called k-fold cross-validation. Oh, this is really, I hadn't anticipated this issue. Let's see. I have a feeling I have to be very careful of what I write because it's going to be here forever. So k-fold cross-validation, you still have your data set. K-fold cross-validation. Yeah. And so you still want to set aside some, here you have features, here you have labels. You decide to divide it rather than like 2 parts in k parts. So this is a number that maybe like 5 or 10. Let's say 5, so at least like I can attempt to draw it. So you have 1, 2, 3, 4, and 5. And so in this case, every train test split that you make is going to be like a 20/80 split. But what you do is like you cycle across the different folds that you made. And so, for example, in iteration 1, this is going to be your test fold, and the remaining 4 are your train set, so all the 4 together. And then you do it a second time. La, 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 la. I don't even know why I got myself into this amount of drawing. 2, 3, 4, 5. And so in this case, basically, like in the other 4 iteration, your test fold becomes respectively the second, the third, the fourth, and the fifth. This is usually after you randomize your data set, because this is like if your data set is in a certain order, for example, objects of a certain class or a certain type are first and other are second, this gives you like terrible results. But as long as your data set is randomized, this means basically that you're running your algorithm 5 times now. So you're building 5 different models. But what you gain from that is that, first of all, once you have like, at least your like 5 scores, 5, 8, 10, at the very minimum should be 3. You get a sense of what's the average performance or the median performance, and you get a sense of what fluctuation you have. So you can put an error bar, and so this is where k-fold CV is okay. And now you're using all the data to build the model. Because you see, like your final model, in your final model, every object has been in the training set 4 times out of 5, and every object has been in the test set 1 time. And so this means that now, you are harvesting your data in a smarter way. And so this is another aspect, the fact that because you have more than one random split, and in fact, you're being fair because you're using every object exactly the same number of times. Now this is a fair representation, so you can trust that what you get as performance is something that is typical. What's the bad side of this? Something that you mentioned already, Mehmet? Yeah. How many times are you doing the thing?
Oh, it's slow.
Right? You're doing the same process 5 times, or 10 times, or 8 times. And so this is a trade-off that may be significant. This is like 8 times slower. Because truly, in every iteration of this process, you're rebuilding your model. And so, especially if you're using an algorithm that is slow, or if your data set is large, that may be like too steep of a price to pay. And so sometimes, like in general, you can imagine, every time you want to do statistics, even small number statistics, you would like this k number to be closer to 10 than to 3. But sometimes you just can't afford to, for your algorithm to take 10 times longer, and so you want to settle with a smaller number. But in general, it's a good practice. Another thing that you can do, and I don't know if you guys want to talk about this more in detail or to see some code. Let's see what time is it? This says 8:53, but I'm pretty sure that 10.
10.
Oh, 10, okay. So another thing that k-fold cross-validation is good for is if you have a model that takes parameters, and if you want to tune these parameters. And actually, this is a bit trickier. So what you're trying to do is saying, okay, say that we're going to work with the decision tree, which is one of my favorite models because the model is very easy to understand, even if it has its limitations. And so in a decision tree, basically you keep asking questions, and every time you ask a new questions, you divide your data set in smaller and smaller splits. And so I don't know, you can have parameters such as, like how deep should my tree be? Or, how many examples do I require in order to make a split in a certain node? Or, how much better of a response am I expecting every time I make a split to make it worth it? So these are, example of parameters that you may want to play with. And so cross-validation also helps with that, because again, you can use this process to find the best model, and you want to repeat it a bunch of times so that again, you make sure that the parameters you're choosing are the ones that typically work best. One thing that is tricky is that you cannot, at the same time, tune the parameters using k-fold cross-validation and report the generalization error. Because if you're choosing the parameters that give you the best test scores, this means that there is leakage of information between the parameters that you're optimizing here and the scores that you're here. And so this is not a fair representation of how the model would fare with those parameters with new data, because on new data, you're not setting the parameters, right? And so the process, you can always do this to find optimal parameters, and given your learning set, this is the best you can do, right? You can choose the parameters that systematically give you the best test scores on your 5 or 10 folds. However, if somebody asks, okay, how do you expect your model to fare on these new data for which parameters have not been optimized, then this would be too optimistic. And so the process of optimizing parameters and quoting a generalization error requires something called nested cross-validation. So basically, you have to go inside your train set. And here, you create also like an inner train and test set. You optimize your parameters in your inner train set. You look at the scores in the inner test set. And then you report the scores that you obtain on this fold. Because these are the only ones that have not participated in your parameter optimization process. So this is just something that, I want to quote because I feel like, in lots of online material, I feel like it's not explained. I feel like if you ever deal with a parameter tuning problem, you have your algorithm and you want to tune its parameters, it's all fair to do it by this, but the test scores that you will get are not fair. And so you have to go through this extra step, and I have code. If any of you is interested, I have plenty of code for all these things that I'm happy to share with you. All right, what else? We talked about cross-validation. Okay, now we are in a better situation than we were here, because we haven't just built a model, but we have built a model, and we have used cross-validation, so we actually know what the generalization error for this model is, which is the test scores. Built the model, and k-fold CV, and have test error, which is what I call generalization error, right? Your best estimate for what the model would do on new data. So what should you do next? I guess that there are two cases. One, your test error is tiny. So you're super happy, I'm done, I'm gonna go. Typically, as I'm sure you know, this is not the case. And so I feel like something that is useful potentially to look at is that, okay, once you build your model, how do you diagnose it to understand how you can improve? And so the next thing I want to talk about briefly is how can you figure out what's going wrong in your model so that you know where there is room for improvement. And the typical, the way in which a machine learning model is diagnosed is by looking at these two flows, which are bias and variance. So in general, if your algorithm has high bias, it means that it's too simplistic. You're modeling, even if you're not writing explicitly what that relationship should be, you're modeling somehow your input-output relationship. And if your algorithm is not able to handle it correctly, then what you can expect to have is low scores. So this is how you would see it. So we're going to have some data are the same in both cases. And so let's say that the data I have something that looks like this. And in black I have my learning set, and in red I have my test set. And actually actually. I do it like, sorry. So, in case of high bias, is that, this is probably something that, at least to me, or, like it was meant to look like something you could fit with a second order polynomial, right? Something with a certain features. Now, let's say that you're using linear regression, which basically only allows you to model linear relationships. So, given your training data, which are the one in black, you build a relationship, you will find probably something like this. And so, once you go and check your test error, you'll probably find something that is fairly low, because this model is not a good representation of your data. However, just because of the nature of the model and the data, you don't really feel like you're not going to really see a big difference between the scores that your models achieve on the training set, which means, if you apply your model to predict the output for data that it has previously seen in the model building, and on your new data, which are the test data. So in this case, like a high bias algorithm, which is sometimes also called underfitting. To diagnose this, you always look at the train scores and the test scores. Train scores meaning how your algorithm fares when it's asked to predict the labels or output for the train set. And this is like the prediction on the test set. And in this case, you expect them to be similar, but low. And if you're looking at an error, you will find that the error, if as a scoring you're looking at error like the mean square error, for example, you will find that your algorithm performs similarly on the train and the test set, but your scores are not satisfactory. So this, if you see this happening, this may be a sign that you are in a high bias case. And so you want to, like take a fix that basically tells you, okay, I need maybe to add more features, to engineer my features so they can represent more complex relationship, or maybe I need to switch to a more complicated algorithm, something that I can handle this relationship. On the other side, on high variance side, we have still same data, hopefully. And then you have the test data. So a typical example of high variance algorithm is like now, if you try to fit this data with fifth degree polynomial. Notice that you have like 5 points in your learning set. So if you use a 5 degree polynomial to to fit this data and this relationship, actually I should have made them, let me put this a little bit higher. So what you will see here is that your model is going to be able to fit the training set perfectly. Whatever score you use is going to be 1, right, or 100%. However, what you will feel and what you will find and what's the typical sign of a high variance case is that your model is excessively tailored to the training set. And so the training scores are high. Actually, I should say that just as a sign, and this is called overfitting. What you will find is that there is a large gap between training and this is how you would diagnose overfitting. So you're not really looking at how good they are. You may decide that in the end, the test scores is what matters. Right? So you may decide. But for the purpose of diagnosis where you can improve, this happens. So in this case, what should you do? Difficult things are you may want to get rid of some features. And again, this like if you're using deep learning methods, typically like this part is handled fairly well by the algorithm. But for many of the simpler ones, you may want to, what you need to do here is like reduce the complexity of your algorithm. It could be using fewer features. It could be using a different algorithm. It could be tuning parameters until, like using the parameters that you think will help making your algorithm less complex, so it is sort of reduces its attachment to the training set. But all in all, the reason why this matters is because, mathematically speaking, at least for some types of loss functions, which measure, like your errors, you can actually have a decomposition of your error as noise plus bias plus variance. And actually here I should say generalization. So the reason why looking at these things is helpful is that, well, the part of your algorithm that depends on noise purely, it's intrinsic in the data, you can't do anything with that. But these other two things, they're here as a trade-off relation. And so this means that if you can diagnose whether this term is dominating or this term is dominating, then you can take steps to improve a relationship so that your total generalization error, which in the end is what you care about, may benefit from a different balance. And so because of that, like looking at, like once you have your test error, looking at these kind of things can tell you what's a step that you can take next to get a better error up. So far so good? Questions? Comments? Okay. So I have, let me see, I need all my energy to raise this, so maybe I actually, so here is, so here is a question for you guys. So what model is variance? Variance. Which one of these is a better model? High bias, low variance, high variance, low bias, lowest gap between train and test scores, or highest test scores?
None of them.
No, there is one.
Number 3.
That's any other votes?
If you have a low gap between the train and test scores, can you still be stuck in a high bias situation?
Sure can. So I always find it that this question is like, confusing for most people. The answer is number 4. In the end, all you care about is your generalization error. The whole purpose of this is just that, if you want to improve on this, then, diagnosing what are the different bits and pieces that go into that number can help you raise it. But, if you have, if you decided that you're happy with a test score of 90%, which is how you expect your algorithm to fare on new data, you just may decide that you don't care at all about, where that 90% number comes from. So, the whole purpose of this discussion is to say, okay, if you want to improve, how can I take it apart so that I can see which part is contributing the most, and maybe I can find a new balance between bias and variance, because they're always trade off for one another, so that maybe your total generalization error is lower, or your test scores are higher. But in the end, when, like if you were to sell algorithm, this is like the one metric that, for science purposes or for commercial purposes, you will care about. Once I give you a new data set in which you only know the features, you don't know the labels, what do you expect? The performance. And finally, I want to mention one last diagnostic tool, which is, let's say that you've done this analysis, but it's not particularly illuminating, or, like you've done this analysis, you find that you are in this two regime, for example, this, but what you tried hasn't really worked much. So another thing that maybe, and I feel like, often it's quoted in the high variance cases, but I don't quite agree. Another thing that may be happening is that you don't have enough data. And, like that's a big limitation, right? As we were seeing here in one of the simple examples, is the size of your learning set would matter in determining how good your test scores is going to be. And so something that you can build easily for these are the so-called learning curves. And so the idea is fairly simple. What you do here is that you have your size of, actually I should say fractional size of your data set. Right? So you can put, I don't know, like 20%, 40%, 60%, 80%, right? And you can see how your train and test scores vary as a function of the size of the data sets. So let's say that we're looking at scores. And so I'm saying score versus error just because, like I want to put train and test. And so in the case of scores, train and tests are always higher, right? Your algorithm has an advantage when it's performing on things that it has seen before. And so in general, your training score, this depends a little bit on what your algorithm is. And so for many of them, what the training score do is they start very high just because, it's very easy to do extremely well when your training set is very small. And then, like they typically, maybe I'm pessimistic here, they tend to flatten out. Once you have like enough data, then really the performance just depends on the algorithm that you have. And then your test scores, on the other hand, typically they will start really low. Oh, the blue one, nice. And so you may find that when you are in this case, this means that you may find yourself in this regime, which means that as you increase the size of your data set, your test scores are still rising. And this tells you that maybe the reason why you're finding a big gap is not high variance in itself, it's the fact that you don't have enough learning data. And so in this case, like after you try different algorithms and optimize that you want, the next thing you want to do is like, say, hey, dear time allocation committee, I am showing you here that I have here, and like my algorithm has this issue, and I've noticed that there's like a large gap between train and test scores, and the reason for that is that I need more training data. And this is how you would diagnose that. I feel like it's something that it is. Vice versa, you may feel, for example, here, when you are at 100%, you see that you are in the regime in which these curves have plateaued already, which means that the scores that you're seeing are a result of the fact that, okay, your algorithm is not perfect and modeling the input-output relationship. This is also fair, but it's good to know that, you shouldn't try to get more data. You should just try to maybe like have more informative features or use a different method. All right. I think that this is all what I wanted to say about general things. So the next thing that I thought we could do is like I wanted to talk about decision trees just because they're easy to understand, one of the most transparent things, And they are the building block for many of ensemble algorithms, like random forests, gradient boosting trees, which are, I feel like, aside from deep learning, some of the most powerful things that people use. And so I feel it's kind of nice to, like see how they work from inside. Do you have any questions up to now? Yeah.
So, in experiments,
Mm-hmm.
you usually don't have labeled data. So how do you?
Right, so in this case, you have another things that now people have started to do is use simulations. Like, for example, there was this like Higgs boson challenge, right, where people, in this case, there were some labeled data, but the problem was like that the Higgs boson event is so rare that you can't, in practice, use data to train your algorithm just because it's such an imbalanced data set that you can't do. And so what they did, like, they had this like big Kaggle computations, like they had these like large simulations, and this is what they used. And so, if you trust enough that the simulations are a good representation of the data, then you are able to use your algorithm on real data with the same caveats, the simulations are never perfect, and because of that, you can never trust 100% that your performance is going to be similar. But I feel like this is also, what we did recently. We did something to sort of get the star formation history of galaxies using convolutional neural networks, and we trained it on simulations. And I feel like, you can do like a lot of things. For example, looking at the representation of simulations and data with some of these methods, like, like dimensionality reductions, visualizations, like to make sure that the distributions that, generate both in observed space are similar. But still, this is the best you can do. And then, but I feel like, a lot of things are going this direction for exactly the reason you mentioned. There are only a few problems, like photometric and spectroscopic redshifts have been like, the sort of like the original, I feel like, application of machine learning to astronomy, just because it's one of the few cases in which, you do have some data that are labeled, because for some data you can have like special observations. But I feel like for a majority of cases, I think simulations are going to be how they're trained. Anything else? All right, so let me see if I can do this. Here. Here. Can you guys actually, I think let me ask you. Okay. So decision trees are, like one of the basics and very nice. And I feel like something that we do a lot when we ask a set of questions, right? So if you have played this game, Guess Who? Oh, thank you. Like early on, like the goal was to guess among this set of faces who was like the card that your opponent had. And so you would ask questions, and of course there are smarter questions to ask and less useful questions to ask if you're trying to determine who is who. So what's the typical first question that you would ask?
Play or go.
Right, and why? Right, because in general, if you can ask questions that tend to split your data set in two, you're maximizing the information gain. Right? It's usually a little bit more complicated than that, and like I will tell you about the metrics, but like our intuition, when like if we want to build an optimal tree, the idea is like my decision tree is going to be like the set of questions that I make, and just like when you play, you want to ask like as few questions as possible. Building an optimal tree means that you want to have as few splits as possible and the correct classification at the end. And this means, like the way you can achieve this is maximizing the information gain at every step of the way. And so, let's look now at a very simple data set like this. How many features do I have? 2, right? So I only have like the x and y coordinate. And this is like a simple 2-class classification problem, right? Red or blue. So where would you split?
Next to, I would say.
So would you make like a vertical line or a horizontal line? Horizontal line. Actually, this is like a data set. I have it with a vertical line. I think they're quite comparable. So like, bear with me. Let's say that we make a vertical line first because it's on the slides. Where would we make it?
Separating red and blue.
Right here, here, here.
Yeah.
Now and here. Very good. So, you know, like, I'm telling you, I don't think I'm gonna get out of this alive. The sacrifices for science. So let's say that, you know, okay, we can make, you know, like a template split here. One thing that I hadn't appreciated until later is that one limitation of decision trees is that you can only split along the features, right? So you're not allowed diagonal splits without feature engineering. If you were to propose a feature, which is like, you know, like the ratio, the product, you can. But this is, you know, like an algorithm which feature engineering matters for exactly this reason. Like if you have these two features, you can do like multiple ones, but you're only allowed to do vertical and horizontal splits. So let's say that we made our first one here. Let's say where x1 was like about 0.7. Now the next one will be right, and so we can have it here at about 0.5, and I think you'll agree that. Now what should I say? Should I stop? Should I continue?
You have to split.
Right. Why? What happens if I keep splitting? Right. I would overfit because as you can see, you know, like having made these two, which means that now I have a tree with 3 leaves, which are like the terminal nodes where I decide that I can make a decision, means that yes, my performance is not going to be perfect. As you can see, there are some imposters in each one of the boxes. But if I keep splitting, you can see from here that I will have to make far too many splits before I can classify everything correctly. And, you know, like probably given the nature of this data, we can see that, you know, like the blue objects tend to be in the upper left quadrant and not in many other places, which means it's probably a good idea to stop at this point. Can I, in principle, classify every object correctly? If I am willing to take an infinitely deep tree? Yes. I could keep splitting until every object is in one box. Right? I can have, I guess the mathematics is something related to 2 to the n and the size of the data set, but you know, like if I decide that I'm willing to take an infinite amount of splits, means like I'm not setting the depth of the tree, then you know, I can get everything in its own box, which means that a decision tree can always get a training score of 1. Not all algorithms have this property. However, you can imagine that, you know, if this is like something that is just difficult, it's very unlikely that in your test scores you will have like a blue object just here or a blue object just here. And so you would expect to have large amounts of overfitting. So this is okay, my representation, blah, 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 blah. So to be a little bit more rigorous in how we decide whether or not we should make another split, I wanted to show you just sort of like, you know, the pseudocode, because I feel like it's nice and it's easy. So basically you start from your learning sample, right? And so, you know, your initial learning sample has the one with all of the objects. And then what we want to know is some sort of criterion. And usually to define this criterion, we want to define what, either the purity or the impurity, you know, however, if you're feeling more like a, you know, a half full or half empty type of person of your data set. Which means that, you know, you need some mathematical measure of how mixed the objects in your box are. And so for this, we use, like one of the ones that you can use is the Gini impurity, which is defined as, I don't know if I'll ever be able to erase this part, but you have it also there. So it's basically 1 minus the sum of the frequencies of each class squared. So let's say that, you know, like to have like a simple example, if you have a data set where you have 3 crosses and 4 circles, then the G, like, and you have this in a box, then the Gini impurity of the sample is going to be 1 minus 3/7 squared minus 4/7 squared. right? Because you have like 3 out of 7 on one class and 4 out of 7 on the other class. So this is define how my impurity is. So in general, when you find possible splits, which means that, okay, if your stopping criterion is met, which means that we have to decide beforehand what our stopping criterion is going to be. For example, if the purity in my box is, I don't know, below 0.1, I may decide that for me this is enough and I don't want to continue splitting. For now, if we want like an infinitely deep tree, we'll set this at 0, which means that unless I've reached a perfect solution in which each one of my boxes is pure, which means that its gene impurity measure is 0, right? Because they are all in one box, so it's going to be a 1 minus 1, giving you a 0 result, then I'll keep going. And so in this case, I will look at all the possible splits on all the possible features. For my 2-feature data set, it means like all the vertical lines and all the horizontal line. And I will look at the one that maximizes the impurity decrease. Right? So I have a certain number here. Let's say that, like your worst possible case is 0.5. If you have like an equal mix of 2 classes of objects, like 4 and 4, your gene impurity is 0.5. So you're going to look at all the splits, and then you're going to calculate, you always divide in 2 boxes. So you're going to have like a left and the right box. You calculate the impurity of the first, the impurity of the second, and you weigh them by their size. Because of course, it's always very easy to make tiny pure boxes, but they don't count much in the overall decrease. And so if you see that from that 0.5, you're moving down to like, 0.4, that's, a significant decrease. And so when you look at all the splits, you look at the split that maximizes this decrease of impurity. And so you get 2 more boxes, the left and the right, and you basically apply the same function to each one of them. And that's the code for decision trees. Okay, so this is the end of my slideshow, but I thought that it would be fun to try and build a decision tree, now that you know. So I made this nice,
But so can you go back to the previous slide?
Yes, of course.
So you initially split in the preview. Sorry. You initially split here in the vertical and then in the horizontal.
Yes.
But it wouldn't be better initially to split in the horizontal?
Just because you feel like it's a bigger data set?
Yeah, I think so, no?
Well, I guess that we will need to look at the numbers. I was thinking about it, but basically what you get here is a slightly bigger data set, but you have 1, 2, 3, 4, 5, and I don't know how this would be, like 6 objects that are misclassified, and this one is slightly smaller, but it only has 4. So my guess is that when you consider the relative volume and the number of misclassification, this one has a slight edge. There's also another thing that, as we will see here, actually, they may be that the 2 are completely equivalent, and in this case, it's just like a random decision. And so I'm not sure in this case how it was, but I guess that we'll need to check whether the extra impurities that we gain with a bigger volume have a larger weight. It's not linear, right, because the impurity goes squared, and the size goes like as a linear weight, and so my guess is that that's what happened. Any other questions?
So when you're recursively looping over the decision tree in the pseudocode, are you always splitting by the same feature? So if the first split was like a vertical line, then the next recursion, then you split the left and right boxes by another vertical line? Or
You can do either vertical or horizontal according to what's best.
All right.
So for example, if you imagine a data set where you have like left stuff on the left and on the right, your best 2 initial splits are going to be 2 vertical lines. You don't have any limitation of which is which.
So the algorithm doesn't decide if he has to split vertical or horizontal. You decide.
No, it does. It looks at all the possible vertical splits, all the possible horizontal splits, and of course, if you have more feature, like all the possible, and find the best. Yeah. I mean, there are some random versions to reduce overfitting. Sometimes you can, split on like a random set of features, or or a random subset. But yeah, sort of like in its original formulation, you just look at the best. All right, so I look at this data set that has habitable planets, and then of course, like I had to heavily engineer. So the data are really these. You can have to actually, if you don't mind passing them around. They're heavily engineered so they're somewhat balanced. And so I'm giving you like a train set and 3 features. So the properties of whether the planet is habitable, and these 3 features that I are the size of the habitable zone of the star, the stellar mass of the host star, and the size of the star in degrees, the angular size of the star as seen from the planet. You all have one? And so I thought it would be fun to take a little bit of time to see if you can, like on paper, build a decision tree. Remember, you can only split along the features, no combinations allowed. And then I'm gonna like put these into scikit-learn and show you what's the optimal tree, and we can like see how you can like open it up to see how which split is made and why. And I put the test set, so you can also put your predictions. So maybe it's fun to see how your algorithm does on the test set. And of course, feel free to do it together. It's not like talk a test. ideas? Anybody who's brave enough to put the tree on the board?
We have something like
Okay. Well, you have something. How does your do you know how your tree does on the train set?
what do you mean?
Have you tested, like, you can look at your train set performance, right? You can apply your tree to the train set and see.
I mean, it has been more a mental tree than
That's very good, yeah. The whole idea was like, you never do this exact. Yeah, intuition, yes. This is like the danger, but yes. So what was your intuition? Like, based on intuition, which is the feature that should matter the most?
Angular size of the star.
Right, you feel like, okay, I have star in my face. It's not likely to be a good place to live, I figured, yeah. And in some sense, yeah, there's like some degeneracy also between them, right? And math. So anyway, anybody has like a tree that they would be able to say, well, like predict the test set? Or do you want to take a minute to predict your test set so that, like at least I can show you and, you can see, okay, this is what my tree would do?
So I just had a very simple one, that if the star is less than 2 and greater than 0.6, then
If, which property? If
the angular size of the star,
less than 2 and greater than 0.6, okay, yeah, so you have two splits, and what is the accuracy that you're seeing on your train set?
so on my training set, there's one that doesn't fit that.
Okay, so that's pretty good, because I think you have like 18 objects, so that would be like an accuracy of about 94%, I would say. Okay, and yeah, do you have test set predictions?
0, 1, 1, 0, 1, 1.
Mm-hmm. Yeah, sounds pretty good to me, actually. All right, shall we see what scikit-learn does? And I feel like this was fun for me because one of the things that I learned while I was preparing this, is how to visualize the trees, which I thought was like fun. Okay, so here, import big, and then I'm using, I don't know if you guys have used it already, I'm using this like export GraphViz, which is like a package that would actually take your decision tree and turn it into a graph. And then this package that is called tie.class that basically allows you to turn that graph into an image. In case you want to use it again, if you want, I can put this on the GitHub. So, okay, so my train and test were, like the same data sets that I gave you on paper. Okay, and so let's see. Right, so this is, hopefully you can see that, the first few lines, yes, are the same thing that you had. Good. And then, of course, I have to define like, an X train, so like my training features, and so I'm dropping the habitable column. And instead, the habitable column becomes my Y train, which is like the set of the labels for the train set. This is like standard language for all of the scikit-learn algorithms. Typically, you want to provide you have like 4 things, an X train, a Y train, which are like training features and labels, and then the test labels and feature, and you will compare the predictions. Okay, so for X test, this is what I have. See, and this is also what we have. Y test is going to be just like the habitable property from test set that I read. Okay, so I'm going to show you 011, 011. Yeah! So you see, like most of you have managed the rare feat of having a better performance on the test set compared to the training set, which is unusual. But of course, here we are dealing with such small numbers that this is why it's happening. But this is also a good sign because you use probably a combination of the data that you have and also your physical intuition. So I was tempted on not saying at all. I was tempted to not say at all what the features were. Right, because I feel like that angular size from as seen from the planet is probably like something that matters because it's hard to imagine life with a star that looks very large in your sky or very tiny. So anyway, how do we do this in Scikit? So I had imported a package called Decision Tree Classifier. Do you want it to make it a little bigger? I have no idea whether this is okay. And so I'm just saying, okay, and in the beginning, for my model, I'm only setting the random state. The reason for that is that even in the standard decision tree, where basically like you look at all the features and you look for the best split, so it sounds like there is nothing random. Actually, like inside the algorithm, the features are randomized at every step, which means that if there are two possible splits that give you the same impurity decrease, you're still, maybe you will get different trees at every step. So fixing the random state actually helps reproducing always the same. And I'm saying, okay, I'm gonna fit my X train and Y train. This is the step in which scikit-learn actually builds a model. So you can see that it's really easy. All right? And so these are like the parameters that I have. And note that, like at standard value, the maximum depth of the tree is none, which means that basically we'll keep splitting until the stopping criterion is set, and the minimum impurity decrease here is 0, which means that basically it will not stop until it reaches completely pure samples, which probably, if you want to avoid overfitting, is not a great idea. All right, and so here, this creates like an object that is the model. And then from here, in this part, what we are saying is like we are exporting it to a graph. And then this command here, i.plus.graph from .data, this is what generates an image. And this is the tree. Now let me make it a bit smaller. So this is the tree generated by scikit-learn. So you say like that the first split was on size from planet. So I think like most of you had it right, and it decided to split at 3.337. Now the way that these things are written, I think are they're a bit confusing because like they should first tell you okay where you are and then what split you're making. But in the first sample you had like 18 objects, and 7 were in one class and 11 were on the other class, which gives you a gene impurity of close to max at 0.475. And like there is no mystery here. Like really, that numbers. You can get it if you do 1 minus 11, 18 squared minus 7, 18 squared. This is like the initial impurity of your sample, and if you do this, you get 0.75. Okay. And so the next split is done on this value from size from a planet, and I have a graph, so we'll see it in a moment. But you see that what happens next is that you get one set, all the objects for which like the angular size was larger than this value. So this is like not too far from the 2 that you had, for example. This gives you like a pure sample with size 5 where the gene impurity is 0. So these are all not habitable planets. And so this is like a sizable increase because it comes with a weight of 518 and it's bringing you from 0.475 to 0. And then on the other side, you're also not doing badly because you now have samples of 13 objects, and there's only 2 objects that are in the wrong class of being not habitable. So even if you stopped here, you see that you're not doing too poorly. Anyway, the other split, as you can see, was on the same property. So again, somewhat similar to what you did. You had the value of 0.6, they were splitting on 0.31. It may end up being like a very similar split, like meaning that you're discriminating the same objects. And if you do this, you see like there's really not too much of a chance of improvement because you're already in a situation in which you have like 2 and 11. So you're able to single out 1, and you're left here with a samples of 12 objects, 1 in one class, 11 in the other. And then from here, you do 1 extra, which is actually not great, because see, like after this, you're still in a situation where you have like a smaller sample, so you're decreasing the impurity, because this is like an impurity of 0.5, being 1 and 1, but it's a very small box. But then you still need another one if you want to get 0 impurity on all the samples. And like here, it's a little bit bigger again. So here this is I was trying to make it bigger. Okay, so this is the representation of the data set. It's actually a 3-feature data set. And am I pointing the right thing? Yeah, stellar size from 5 degrees. And this is just like the other feature that was actually involved in a split, in the third split, which is like the size of the habitable zone in astronomical units. And so you see here, like I put different colors, hopefully you can see that for the objects. And then we can see like one at a time. The first split is here, right? And then the second split is here. This is like this dashed line. You can see that probably like even one split is not her. The second split, just to go back to one of your questions, like okay, it's another vertical line. They decided that this is like the most convenient. And then the third split is an horizontal one. Notice that actually, it happens only in this box. Like each box is split and becomes independent from the original sample. And then the last one is here. But you see that basically these last two splits have just like singled out these points. And so it's a pretty high price to pay to have like two extra splits to single out one object, and almost never a good idea in terms of generalization error. Now, of course, we are working with a very small data set. So here I try to add the object from the test set. Let me see what's here. It's hard to see. They are squares. So there is one here. So this is already showing you that this object will be misclassified in this. But this is an object that actually, because we had like cut out this as our first split line, this was an object that was difficult to classify anyway. You see that the stellar size from the planet is actually pretty large. So this is like a tough mistake to correct, just because this object lives in an area where many of the habitable planets live. And then you have like some more squares here that are habitable, that look like will be classified correct. And so if I want to look at my performance, let's say accuracy, which is just a percentage of correct classification on the train and on the test set, this is what I can do. And in this case, I'm getting 1, of course. If I don't set the maximum depth, I'm always going to get 1 for the decision tree. But a considerably lower score on the test set of 83%. Namely, the test set is only made of 6 objects, so this means 1 misclassification. So we can't trust these numbers really, but this is what high variance looks like a significant gap between your train and test scores, and this is how you would see. So I could, for example, make another model in which I set the maximum depth of the tree to be 2, which means that I'm allowed a maximum of 2 splits. And I'm still keeping the same random state, just so I know that it's basically just a truncation of the previous one. And so in this case, I end with this, which is a more reasonable tree to have. And for this model, now I have 94% in training scores, right? Because I've truncated it, it doesn't do as well, but the same accuracy score on test scores. In this case, I haven't improved this just because the numbers are so small that 1 misclassification always gave me the same numbers. But this is how you would go about reducing overfitting. One of the possible things that you do is reducing the depth of your tree so that maybe it doesn't do as well on the training set, but it can generalize. And I think that's all. So if you guys have any questions, or if you want to have this code, so you can plot your own decision trees, I'm happy to share them, and